So we are told in this problem that we have copper. Copper exists in two primary isotopes, copper 63 with an atomic mass of 62.9296 AMUs, and copper 65, which exists at a mass of 64.9278 AMUs. We want to know what the average atomic mass is. Now, the most common mistake that students will make is if they completely ignore the abundances here and just take a straight up average, they'll get an answer that looks like it makes a decent amount of sense. After all, if I take 62.9296 plus 64.9278, put those together and divide by 2, 62.9296 plus 64.9278, I get 127.8574, which if I then divide by 2, gives 63.9287. And if you do that, you go, okay, well, that's not too far off from the periodic table. Okay, I probably did it right. The problem with that is we've completely ignored the fact that some isotopes are more stable than others. And some isotopes are going to be much more prevalent than others because of that stability. That's where the weighted averages come in. So what I need to do is I can't just simply ignore these values. I need to use them. And so there's a number of ways that you can do this. You can take 62.9296 and multiply it by its percent abundance. Now, I'll tell you, there are two ways to go about this. I prefer to actually keep the percentages as percentages here and then divide by 100 at the end. And the main reason I do that is for the majority of my students, converting the percentage automatically isn't something that happens naturally. And so this kind of provides them a fail-safe, because when they get to the end and they see that the answer is in the hundreds or the thousands, they know, oh wait, I need to divide. So what I often do is I'll tell them, okay, let's multiply by the percent. So 62.9296 multiplied by 69.17% gives me 4,352, 53. And yes, we are going to carry our significant figures here. I also see that if I have 64.9278 multiplied by its percent abundance. Now, its percent abundance is dependent upon the other. So if 100% of it is these two isotopes and 69.17% is the first isotope, then the remaining isotope is the rest. So 100 minus 69.17 is 30.83. And so 64.9278 times 30.83 is 2002. And so now I add those together. 4353 plus 2002 gives me 6,355, which I divide now by the 100 since I had it as percentages instead of fractions. I get 63.55 AMU as the mass. So again, the reason why I do it this way, why I divide by 100 at the end, is because especially when we get into smaller numbers, you know, when we have 3% or 1% or less than 1%, the conversion of percent to fraction is not always super transparent and easy to see. And it's very easy to make those mental mistakes where you say, okay, you know, 1% is 0.1 instead of 0.01. And if you do that, you mess up your decimal place, you end up messing up everything else. It's a lot easier to add these big numbers together and then go, okay, well, there's no such thing as a molar mass or a atomic mass of 6,000. I need to divide by my 100 now. And when you do that, that 63.55, that is the number that's on the periodic table for copper. And that's how you know that you've done it close to correct. You should be really close to that number, not just vaguely in the ballpark. So we have to remember that it's a weighted average when we do an average atomic mass. It's not a straight up average. It's not an arithmetic average.
Mr. Brooke, where did the 30.83 come from?
So that came from the fact that we had 100%, which had to be 69.17 plus whatever the other one was. And so if I take 100 minus 69.17, that gives me my 30.83.
Thank you. Okay.
Okay. Yeah, so a lot of times you'll see this in problems like this where they'll tell you the percentages of one or two of the isotopes, and then the third isotope or the last isotope they'll say is just the rest. And all you have to do is figure out, okay, this is the rest. This is the leftovers. And so I just take 100, I subtract off all the isotopes that I know, and whatever's left over after those subtractions, that's what's left. That's what's the missing one. All right, any other questions? All right. So let's talk a little bit about the periodic table then. And so the periodic table was devised by a number of people, but probably most famously, it's the Russian chemist Dmitry Mendeleev. And in Mendeleev's periodic table, we saw elements that were being ordered by increasing atomic mass. And that left open the room for periodic properties. Now, the periodic table ended up changing over time, where instead of going from increasing atomic masses because of the lack of knowledge of protons, we end up seeing them ordered in or increasing atomic number, where we have arrangements of periods, the horizontal rows of the periodic table, and groups or families, the vertical columns of the periodic table. And so this was kind of the basis of that other activity, the periodic table mystery, which was looking at some of the aspects of the periodic table and how to identify them. Now, we didn't get a chance to talk about this yesterday, so I wanted to kind of draw your attention to a couple of key aspects, key attributes that we should familiarize ourselves with. First of all, there are some common families that we need to acquaint ourselves with. The first of which is group 1, which technically starts with hydrogen, although hydrogen is not considered to be an alkali metal in the pure sense. But group 1 here, these are the alkali metals. Alkali metals are known for having some very interesting chemistries. In particular, they are very, very reactive with air, and they are very, very reactive with water. In fact, the reactions with water can be downright explosive if the circumstances are correct. These are substances that are usually stored in oil or in kerosene or in some kind of otherwise inert atmosphere, because they will react with the oxygen in the air. They will react and rip hydrogen off of water. So we got to be real careful about their storage. Closely related to those, if we go just next door, we have, these are the alkaline earth metals. And these ones are characterized primarily by they are also reactive with the air. They are also reactive with water, but to a much lesser degree than the alkali metals are. The alkali metals are very explosive in their reactivity. The alkaline earth metals are not as much so.
And all of the alkaline earth metals, those all of them have a -2 charge. Is that correct?
Yes.
Okay.
Well, excuse me, +2.
Oh, +2?
Positive
Okay.
2. And we'll get more into the dynamics of that when we get into chapters 3 and 4.
Okay.
But yes, there are some familial traits that we will see in terms of their reactivity, their ability to form ions, and so on.
Okay.
Moving on, let's grab this big group here. Here in the middle, this big group of elements are known collectively as the transition metals. Now, transition metals have a wide variety of reactivities associated with them. Some of these are quite reactive. Some of these are lesser in their reactivity. Overall, they are far less reactive than the alkali or the alkaline earth metals. And the other thing that we should notice about them is that they have some coloration to them. These are metals that have the possibility of not being silver. And when they dissolve in water, can make some really colorful solutions. They have the possibility of having multiple charges. And actually, we'll see that in some ways, elements like tin, lead, bismuth, polonium, tend to act more like transition metals than traditional metals. Tin and lead, for example, are well known for having variable charge. Whereas even with gallium and indium and thallium rather, they tend to focus mostly on +3 charge. You might see them with a +1 charge, but it's a lot more rare. So that's a little bit less common of a trait. On the back side, so looking at some non-metal groups. On the non-metal side, we have the halogens, which is group 17 here. The halogens are kind of the analogs to the alkali metals. They are highly reactive nonmetals. Now that they don't really have air reactivity or water reactivity, but they do have a good bit of reactivity overall. They form a lot of covalent compounds. And that puts them in very stark contrast to this last group. The last group here, which we'll highlight in pink, these are the so-called noble gases. And these are known for their incredible lack of reactivity. Now, there are other family names in here. The oxygen group, for example, is often referred to as the chalcogens. So basically, put a couple of C's in there, chalcogens, for the oxygen group. But the oxygen group doesn't have as much consistency in their reactivity as the halogens do. Yes, oxygen and sulfur, and to a lesser degree selenium, are reactive. In fact, oxygen is the most abundant element in the Earth's crust because of its reactivity with all of the different metals that make up the Earth's crust. But the gap between oxygen and sulfur, and the gap between sulfur and selenium, are pretty large in terms of their overall reactivities. And so sulfur is much more predominant as a stable element in the Earth's crust, just sitting there by itself, than it is as a reactive component. And selenium, it's much more of a trace element. It's present, but in significantly smaller quantities. Now, the last thing I wanted to point out to you, I've alluded to this in the past. I want to make it clear now. There are a series of elements that are naturally diatomic. And they are hydrogen and what I call the 7 that form a 7. So if you look at hydrogen and these 7 nonmetals, starting with nitrogen, working your way down through the nonmetallic or metalloid halogens, these substances are naturally diatomic. And what that means is that these substances will naturally on their own pair up with themselves and as an element exist in a pair. So we don't experience hydrogen as just simply H. Hydrogen always exists in its elemental form as H2. We don't experience fluorine as just F. It always exists as F2. And so when it comes time, especially when we start getting into balancing equations and recognizing chemical reactions, that's an important thing to understand. If I'm given a word equation that says hydrogen reacts with fluorine to make hydrogen fluoride, I have to understand that the hydrogen and the fluorine that we're talking about there are not just H and F, they're H2 and F2. So those substances are the ones that we need to kind of look out for. Because if we fail to recognize that quality, that characteristic of them, we're going to lose something about them. We're going to make mistakes in terms of quantifying their reactivity.
Silly question.
Yeah.
You said that they always basically happen in 2. So why does oxygen and water only have 1 if it doesn't like to be by itself?
Well, so what's happening there is oxygen forms a double bond with itself when it's diatomic. When oxygen bonds in water, it's taking those 2 bonds that it would have made with itself and making 1 bond with hydrogen and a second bond with another hydrogen. So it still has two bonds, now with two different things instead of with itself.
Oh, okay.
So that, yeah, that we'll get more into that level of reactivity in chapter 4, but the overall concept is kind of the same. There is a set number of bonds that atoms, that elements are seeking to make.
Mm-hmm.
And if it can get it from itself, great. If it doesn't get it from itself, then it goes and seeks it out from others. And so basically all that's happening in water is hydrogen is replacing the bonds that oxygen was going to make it to itself.
Okay, so if there's not enough hydrogen, then the oxygen will basically just form with itself then. Like if there's not enough hydrogen in the mix, the oxygen won't have anything to stick to, so it'll just form with itself.
To some degree, yes.
Okay.
It's we're in danger of oversimplifying it a little bit.
Okay, no, that's fine.
But yeah, certainly when we get to chapter 4, we'll get into the kind of the impetus for why do things bond, how do they bond, what's the driving force behind the bonding, that kind of stuff.
Okay.
All right, any other questions here before we move on? Okay, so let's talk a little bit then about some calculations that we can actually do using the periodic table. And so we've already talked about the idea of atomic mass, the fact that the periodic table gives us an average atomic mass that we can calculate from isotopic abundances if we just kind of know how much of each one's present. But we can use that same kind of logic to figure out molecular masses, where all we need to do is, if I know the chemical formula of the substance, I can just add together the atomic masses of all of the atoms that make up the molecule and kind of take it from there. And so from that perspective then, if I know the molecular formula, all I need to do is just look up what the masses of each of the atoms are. So take, for example, ammonia here. Ammonia, NH3, has 1 nitrogen atom and 3 hydrogen atoms. So if I take the mass of the nitrogen atom, which is this 14.07, and I take the mass of 3 hydrogen atoms, each one being 1.008, then the end result is I get these together, and the overall mass of the molecule would be 17.09 AMUs. Now, the same thing can be done for ionic compounds as well. Now, technically speaking, ionic compounds don't form molecules. Their arrangements are a little bit more complex than that, because you've basically got this large array of ions that are all alternating in this large crystal. And so we tend to call those formula units. And so the technical term, instead of molecular mass, would be formula mass. But same kind of principle applies. I've got the molar mass of calcium, which is 40.08. And the molar mass of chlorine, which is 35.453. And there are 2 of them because there are 2 in the formula. And so if I take that and add 2 of those to it, I get 110.984 as the atomic mass for the formula unit of calcium chloride. Now, this is all well and good, assuming that we are actually dealing with individual molecules or individual formula units. Problem is That's rarely what we're actually doing. And so what we have to do is we have to start to look at things from a broader perspective. If we're doing any kind of chemical reaction, if we're doing any kind of work in our laboratory, we have to understand, okay, there's a problem with our setup. I'm not going to be able to measure individual molecules. And so this is where a mole comes in. Now remember, mole is one of our base units in the SI system. And the mole stands in for this number, Avogadro's number, 6.022 times 10 to the 23rd particles, or formula units, or molecules, or atoms, or whatever the case may be. Now, the number here is derived. We are working off of the assumption, and again, I've made this case before, I'll say it again. Every single unit starts with some definition somewhere. And so the definition for the mole and the definition for AMU have the same origin. That is, it is that many atoms in exactly 12 grams of carbon-12. Remember, our AMU was defined by 12 grams of carbon-12, or 12 AMUs of carbon-12, being the definition for a molecule. Well, now 12 grams of carbon-12 is being the definition for a mole. And so 1 mole is that many particles. So there are Avogadro's number, 6.022 times 10 to the 23rd atoms in 12 grams of carbon-12. There are 6.022 times 10 to the 23rd atoms of carbon-12 in 1 mole of carbon-12. And so every other determination of the number of molecules, every other mass is based off of those determinations. But one of the really great things about using this conversion is by converting things into moles, we now have a consistent way of comparing one set of objects to another. Because if I have 1 mole of carbon and 1 mole of nitrogen, I know that those 2 samples have the same number of atoms, have the same number of molecules or formula units. If I can get it down to moles, I know I can compare them directly. Whereas if I'm comparing masses, a mass, 100 grams of iron is going to have a much different perspective than 100 grams of hydrogen. 100 grams of iron is only going to be a little less than 2 moles. 100 grams of hydrogen is going to be almost 50 moles. And so the number of particles that I get in the one sample versus the other are vastly different. And that's going to play a considerable role in how we determine how much each of those substances can react in different chemical reactions. So we use the mole as kind of this key conversion point where we can compare the amounts of things available in our chemical reactions directly. Whereas grams are easy to weigh. It's an easy unit to measure, but it's not considerably accurate in terms of how many particles we're actually dealing with. Whereas moles gives us that number. And so from that perspective then, we can use Avogadro's number as a means to compare the number of particles of something and the number of moles of something by simply using Avogadro's number as a conversion factor, just like we did in chapter 1 with using conversion factors to go from grams to pounds or liters to milliliters or anything like that. So let's take a look and do a quick practice problem. If I have a sample of 2.59 times 10 to the 18th formula units of calcium chloride, how many moles are present? Well, to do this problem, I'm going to need to take that starting material, 2.59 times 10 to the 18th. And actually, for simplicity's sake, I'm going to use scientific notation here, the kind that your calculator gives. So capital letter E is going to stand in for this 10 to the negative 18th, or 10 to the, or times 10 to the part. Okay. Now I'm going to do that conversion. One mole of calcium chloride is equivalent to 6.022 times 10 to the 23rd formula units of calcium chloride. And so we can see that my formula units cancel out. I'm left with just moles. I bring out my calculator, 2.59 times 10 to the 18th divided by 6.022 times 10 to the 23rd. And I get 4.30 times 10 to the negative 6th. And that is moles of calcium chloride. Okay. One quick but really important note. If you do not know how to use the exponent button, this is not showing up the way it should wanted to. If you don't know how to use the exponent button on your calculator, hit me up. I will try to help you as best as I can. If you have a TI model, it's going to show up as an EE in one of your secondary functions. If you have a Casio like I do, it's going to be the EXP button, which is this one right here. But what that does is that saves you from having to type in times 10 to the caret, saves you from having to put in all the extra parentheses and whatever, because if you don't do this step, if you make a mistake, like say you forget a parenthesis or you put it in incorrectly, what happens is it'll interpret this as 2.59 times 10 to the negative 8 or 10 to the 18th divided by 6.022 times 10 to the 23rd, and you'll end up getting some sort of number times 10 to the 40th. So if you're not familiar with how to use your calculator to do scientific notation, let me know. I'll try to walk you through it separately here, at least as best as I can with what I have to offer. But it's really important that you know how to use your calculator, especially for these kinds of functions. Scientific notation can be brutal on your calculations and lead you to quite a few incorrect answers if you don't treat it properly. So if you have questions about that, please let me know, and I'll try to give you some more individualized help in a later session. But for right now, let's go and move on to talking about molar mass. Now, molar masses take that idea of the mole, take that definition of Avogadro's number and the 12 grams of carbon 12, and apply it thusly by basically saying that I don't need to do any manipulation to the periodic table values. The definition of Avogadro's number, the definition of an AMU, basically caused the Avogadro's number and the AMU conversion to grams to cancel out. So the number of AMUs that an individual atom has is the same as the number of grams an individual has if we're talking about moles. So the way that we calculated molecular masses or atomic masses or formula masses is the same. The only difference is instead of talking about things in AMUs, we're going to talk about them now in grams. So just as an example, an atom of helium, according to the periodic table, weighs 4.003 AMUs. A mole of helium weighs 4.003 grams. And so that is its molar mass, 4.003 grams per mole. And so what this allows us to do, and I like these kinds of visualizations, by the way. You're going to see a number of different kinds of visualization maps from me throughout the course of the rest of this semester. And the reason I like these is it's very easy to kind of follow to figure out what I need to do. And so I use these often as roadmaps, tools to help me to go between one substance and another, or to help me figure out how to frame my calculations so that I end up with the right substance or the right calculation in the end. And it works something like this. Let's imagine for a second that I needed to calculate the mass of a compound based upon the number of atoms of a particular element. So let's say I want to go from, number of carbon atoms to grams of carbon dioxide. Well, the approach that I would end up taking is that I would need to start here with my atoms. I would need to go up and calculate the number of moles of carbon that I had. I would use the chemical formula to go from moles of carbon to moles of carbon dioxide. And then I would use the molar mass of carbon dioxide to figure out its total mass. And so if I follow along here, I can see that my first step would be to take atoms and divide by Avogadro's number to figure out the number of moles. I'd use the chemical formula to say, okay, every carbon dioxide has one carbon in it. And then I'd use the molar mass of carbon dioxide to convert from the moles to the grams. So I could do this from a number of different perspectives and a number of different starting points. All I needed to do is this basically just helps me to organize my calculations moving forward. So this is a really powerful tool, and we're going to see it used in a number of different cases along the way here, especially when we get into the more calculation-driven chapters, like chapters 7, 8, 10, 11, and so on. Let's start off with some practice problems, and then we'll take a short break. So how many moles of ammonia gas are present in 24.92 grams of ammonia? Now, if I go back to I have a mass of ammonia. and I'm trying to convert it into moles. So I know to do that, I'm going to need to divide by the molar mass. And so really the only thing that I need to do to solve this particular problem is I need to find the molar mass. So molar mass of ammonia, ammonia is NH3. And so I have 14.01 grams per mole for nitrogen. I have 3 times 1.01 grams per mole for the hydrogen. So my total mass is going to be 17.04 grams per mole of ammonia. Now, using that map on the previous page, we can either just simply divide this, or if we take the more dimensional analysis type approach, 24.92 grams of ammonia and using that molar mass as a conversion factor now, 17.04 grams in 1 mole. And so now I can see my grams are going to cancel. 24.92 divided by 17.04. I get 1.462 1.462 moles of ammonia. And so that's really all that there is to this particular type of example. Any questions?
Nope.
No. No.
Okay. And so let's take a break then. Let's come back in about 10 minutes. So let's say about 10 after 10, go ahead and get up and stretch and move around. And we'll come back in a few minutes.
All right, sounds good.
Okay, so we're back. Now before we move on to the last one here, the last bit, we're going to look at, let's just do one more practice problem that's a little bit more involved, a little bit closer to what you would see on the homework. And it's a question like this: how many nitrogen atoms are in 85.11 grams of dinitrogen pentoxide? Now, again, the way to kind of focus this, the way to organize this would be to go back here and look at, okay, I'm starting with a massive compound. And I want to take it all the way to atoms of an element. So there are a couple of steps that I have to go in. And so the way I can look at it is that each one of these line segments represents an individual calculation that I'm going to have to do. So I'm going to need to do a conversion or a calculation to go from mass of compound to moles. I'm going to have to do a calculation to go from moles of compound to moles of element. I'm going to have to do a calculation or a conversion to go from moles to atoms. Now, since all of these are essentially conversions, the easiest way to go about doing this would be using dimensional analysis. So taking that Q, if I start with my 85.11 grams of dinitrogen pentoxide, my first step would be to convert the grams of this substance into moles. Now, the way to do that is with a molar mass. Molar mass of dinitrogen pentoxide, mass of nitrogen is 14.01, and there are two of them, so 1401 times 2, plus oxygen. Oxygen is 16.00 times 5. I get 108.02. .02 grams for every mole of dinitrogen pentoxide. So my grams have now canceled. I'm left with moles. Now the second conversion here, I want to go from moles of dinitrogen pentoxide to moles of just straight up nitrogen. For that, that's where the chemical formula comes in. I know that for every one of these, I am going to get 2 nitrogens. And so my moles cancel out. I'm left now with just moles of nitrogen. And then the last step, I want to go from moles of nitrogen to atoms of nitrogen. And this is where the Avogadro number comes in. 1 mole is 6.022 times 10 to the 23rd. And so my moles of nitrogen cancel. And now I do my calculation. 85.11 times 2 times Avogadro's number divided by 108.02 is to 4 significant figures. $9.490 times 10 to the 23rd atoms of nitrogen. And so this is probably about as complex as these kinds of problems can get. But again, if you kind of follow the roadmap that we were put on, in this problem, you can see we've done each of the steps along the way. We started with our mass. We used that mass and the molar mass to convert it into moles. We used the chemical formula to turn the moles of the compound into moles of the element. And then we used Avogadro's number to convert that moles of element into atoms. So every step along the way, corresponded to one of these calculation steps that we did in the dimensional analysis. So it was all done intentionally. It was all done quite purposefully along the way. And so if you're not sure what the next step is to follow, kind of keep that in mind. Keep in mind that you've got these things in place that'll allow you to do these steps in particular, and allow you to kind of organize yourself to make sure that you're doing the correct calculation steps. All right. Any questions or thoughts before we move on?
Yeah, no.
Okay, so the last topic here in chapter 2 concerns kind of a pairing of sorts. Technically speaking, if you look in the textbook, the concept of empirical formula and percent composition really doesn't make a full-on appearance until chapter 7. One of the reasons we're including it here is because it's kind of a natural next step from the calculations that we just did. Because using molar calculations, being able to convert between grams and moles, being able to go and look at percentages, really follows from what the last couple of calculations that we did. So we actually kind of depart from the way that the book presents things here in order to give you an opportunity to do some more higher order or higher level kinds of calculations, which will certainly help you in the laboratory when we go to do the empirical formula lab, which is actually, if you look on the syllabus, that's today's lab in the series. So percent composition. We use percent composition as a means of describing in what way are different elements represented in a given compound. And we always do it in the matter of mass. So the mass composition, the percent by mass, is what tells us, okay, this particular compound is 30% this substance and 30% that substance and 40% this element. And a classic example of this are if you dig up the earth, what you'll find in a lot of cases, especially here in Indiana, there's a good composition of iron in our soil. And the iron-containing compounds, there are many. Two of the more common ones are woostite, which is iron 2 oxide, and hematite, which is iron 3 oxide. Now, the way that we can look at this from a constituency kind of standpoint is that we can look at woostite and say, okay, in terms of a molar ratio, in terms of an atomic ratio, we've got a 50-50 blend. Iron is half and oxygen is half of the atoms in woostite. And in hematite, it's more of a 60-40 split. There are 3 oxygens for every 2 irons, so 60% of the atoms in hematite are oxygen, and 40% of them are iron. And from that atomic standpoint, yeah, we get some kind of an idea, but the mass standpoint is going to be even more telling. And let's take a look at it. The percent composition by mass of iron oxide. So what we have to remember, the molar masses here are going to become important. For iron, it's 55.85 grams per mole. For oxygen, it's 16.00 grams per mole. And so from this perspective, if I look at the percent composition, we can characterize percent of X, whatever X is going to be equal to the mass of that element.
Mr. Bruck, do you always, okay, you rounded. Well, yeah, you didn't put 15.999.
Okay, so this is a good secondary question. When it comes to molar masses, generally speaking, we can get away with rounding to 2 decimal places. Now, there was a point that someone, I think it was Malaz, made last week about not wanting your conversion factors to limit your significant figures as much as possible. And certainly that applies here as well. So if you're in a situation where you have more significant figures in your masses, then you may have to use more than 2 decimal places to cover for that if they're available. But generally speaking, we tend not to have too much that has more than 4 significant figures. So we usually can get away with two decimal places for that reason. In the case of oxygen, I think it's like 15.9996 or something like that is its molar mass. So even if we carried it out to 3 decimal places, it would still round up to 16. And so from that perspective, yeah, we're usually okay. Now, if you want to add a 3rd decimal place or a 4th decimal place, you can. It just at some point it becomes unnecessary. It becomes redundant. The difference in that last decimal place really isn't going to affect your calculations too significantly. Other than with significant figures. But no, that's a good question. That's a good point that we need to kind of clarify, because otherwise, some people round at 1 decimal place, some will round at 2, some will just just take the first 2 numbers and go with it. And that we do need to try to be standardized, at least in some way. And so, like I said, a good rule of thumb is 2 decimal places. You really can't go wrong with that, unless you just have really, really precise data and you've got 5 or 6 significant figures to work with. So again, coming back to what we were looking at originally here, our formula for calculating percent composition, the percent of X is going to be equal to the mass of X, whatever that element is, divided by the total mass of the compound, and then multiplied by 100%. So from that perspective, then, the percent of iron is going to be equal to 55.85 divided by the total mass. Now the total mass here, 55.85 plus 16 would be 71.85 grams per mole. So divide by 71.85 times 100%. And so that would equal, so 55.85 divided by 71.85 times 100%. 4 significant figures, we get 77.73% iron. So in this case, even though the molecular or the atomic split is 50-50, the mass split is 77.73% iron. So the mass of the iron does make a considerable difference in terms of how we would view the percent by mass composition. Now, ordinarily when we're asked to do a percent composition for a compound, we need to factor in all components of the compound. So we need to do percent oxygen as well. And so we could calculate this the same way. Mass of oxygen is 16. Total mass is still 71.85. And if I do that calculation, 16 divided by 71.85, I would get times 100%, 22.27. Now you may be saying to yourself, well, isn't there an easier way to do this? And the answer is yes. Similarly to what we did in the very first practice problem that we did today with the percent abundances, the rule of 100% applies here as well. I could have done 100% is equal to the percent of iron plus the percent of oxygen. And since we knew that the percent iron was 77.73%, we could have done that subtraction and come up with the same 22.27% oxygen that we came up with here. And so keep that in mind, that that is always an option once we get to the last element of a compound, is we can always figure out the last component by subtracting all of the other components from 100% instead of doing the calculation this way. And especially if you have a 2-element compound, that can make it a lot easier, because ordinarily it's not too difficult to subtract something from 100 and figure out what the remaining piece is, as opposed to doing all of this fractional business. All right, any questions?
Yes. So, what if? Okay, so do you not add the 2% of the iron and oxygen? Like, you don't add that, and that'll be your answer because it said percent composition, or they want to know by each element?
They want to know each element individually. So when it asks for the percent composition of iron oxide, what they're looking for is how much of it is iron, how much of it is oxygen. And so the way that you would answer this is iron 2 oxide, FeO, is 77.73% iron and 22.27% oxygen.
Okay,
That's its percent composition.
Have you ever seen it where it's like, what, Fe3O? Do you need to multiply 3? Like, take the molar mass for Fe and times it by 3 if it was 3 of them?
Yes.
Oh, okay.
So all that you need to do is, I think I've got another practice problem in here that's like that. Let's.
Oh no, I don't want to throw you off. I got it in my head.
Okay.
Yeah. You say yeah.
But no, the answer there, you're correct. Okay. Whatever the component is that we are looking at, that's how we're going to approach it. So let's just say, for a matter of clarity here, we won't follow it through all the way. But let's just say, for the sake of argument here, that our compound was actually the other one, the hematite, the Fe2O3. Well, if that was the case, then we would approach it in a very similar kind of way. The only difference would be that we would have slightly different molar masses to consider in that denominator, and we would do the numerator slightly differently as well. So 2 times 55.85 plus 3 times 16, 159.70. So, like I said, the only real difference there is the approach. So my percent iron, similar kind of concept. It would be, since there are now 2 of them, it would be 2 times 55.85 over the 159.7 times 100%. And so 2 times 55.85 divided by 159.70 times 100%. We would get 69.944. And then using our subtraction rule, you get 30.056 as the percent for oxygen. And so calculation is essentially the same. It's the same process. We just have to apply the concept of the formula to that calculation. That's all.
Okay.
And so that's pretty common. So if you'd done the calculation for oxygen, it would have been 3 times 16 in the numerator instead of just 16. That'd be really the only difference. Any other questions?
No.
All right, then let's move on to talking about empirical formulas. So an empirical formula is a formula for a compound that shows the ratios of each element in that compound in the lowest terms possible. Now, this is different from a molecular formula because a molecular formula tells you the actual number of atoms of each kind of element. So an empirical formula could be a molecular formula, but then again, it could be just a condensed version of a molecular formula. And so what I mean by that is let's take, for example, a really common molecular compound. Glucose. So glucose, simple sugar, has a molecular formula of C6H12O6. That's its molecular formula. That's what its molecule looks like. If I look at that molecule, I'm going to see 6 carbons. I'm going to see 12 hydrogens. I'm going to see 6 oxygens. Now, the empirical formula for that is not C6H12O6. It's going to be the lowest terms ratio of each of those elements to each other. And so what you should be able to see is that each one of these numbers here is actually divisible by 6. So the empirical formula here is actually CH2O. This is the lowest terms ratio. Now, you might be asking yourself, well, why would anyone do an empirical formula? Well, the reality is when we do elemental analysis based upon percent compositions using techniques like mass spectroscopy or other spectroscopic techniques like GCMS or LCMS, empirical formulas might be the only thing that we have to go on. We might only know the percent compositions of one element to another, and we won't be able to determine the actual molecular formula until we see how big the compound actually is. And so empirical formulas are often used as a marker, as a benchmark to kind of give us, okay, this is the rough idea of what we have. We know we have this ratio of elements, 1, 2, and 3. And that's going to give us kind of the base, the starting point to figure out what it is that we have. And then once we know a little bit more about the compound, then we can go from that empirical formula to its actual molecular formula and start to think about how it's arranged and what its molecular shape and whatnot might be like. And so the way that we kind of do that is through this formula of conversion, which says that there is a relationship between the empirical formula and the molecular formula. There's a multiplier of sorts. We're going to call that multiplier n. And the way that we find the multiplier is we take the molecular mass that we have obtained by some other type of experimentation, and we divide that molecular mass by the mass of this empirical formula. And theoretically, the number here should come out to be pretty much a whole number. And that whole number we can then multiply by my empirical formula to get the molecular formula. So let's see this in action. Now, a couple of things about empirical formulas. There are a number of ways to get them. One of the ways is by taking percent composition data, like we just saw, and then converting it into moles and converting it into an empirical formula. The other way is using experimental data, where this is what your lab will focus on. You'll use experimental data to figure out how much of each atom, or excuse me, each element that you have, and then use that information to figure out what the actual substance is. So for the empirical formula, using the percent composition technique, what you're going to do is you're going to start with 100 grams of the compound. So you take those percentages and you immediately turn them into gram values, because percent just means part of 100. So if I have something that is 70% carbon, I'm going to make that 70 grams of carbon. If I have 30% oxygen, that's going to be 30 grams of oxygen. My next step, using molar masses, I'm going to turn those grams into moles. And then I'm going to start to convert those moles into ratios of each other to find the whole number ratio of one element to another. Now, if this sounds a little bit complicated, it might take a couple of examples to work through to get used to it, but that's what we're here for. So let's take a look at an example here. Now, we've already kind of worked through an example similar to this going the other direction, but let's follow this to its natural conclusion. I have something that is 69.94% iron and 30.06% oxygen. And so what I'm going to start with is I'm going to turn those percent values into gram values, 69.94 grams of iron, 30.06 grams of oxygen. And so again, that was my first step. My first step was to convert the percentages into grams, and all I did is change the unit. The second step is to convert each of these into moles. For that, I'm going to need molar masses. We've been working with iron and oxygen for the entire last hour, so hopefully you've got these committed to memory by now. 55.85 grams of iron in 1 mole. And for the oxygen, 16 grams in 1 mole. And so that is going to equal out, so 69.94 divided by 55.85. 4 significant figures, 1.252 moles of iron. .06 divided by 16 gives me 1.879 moles of oxygen. So after this calculation, it's not readily apparent what the ratio is between them. It looks like it's maybe 1.5 to 1, but we can't really be entirely sure. And so when you come to this point, the thing that you do to help you get this down to low whole number resolution is you have to take the value and divide each of these by the same number. And the number that you're going to choose is the smaller of the two. So 1.252 is the smallest of the numbers. And so that's going to lead to 1 mole of iron. And so the reason we did this, by dividing by the smallest number, we guarantee that that number is going to be a 1. And then from there, we can hopefully get every other one to either come out as a whole number as well, or come out to a fraction that we recognize. And so 1.879 divided by 1.252 gives me 1.501. And we can recognize as that's close enough to 1.5. Now, the mistake that students make in this spot right here is going, well, I need to get whole numbers right now. I have to get whole numbers right now. And so I'm going to round that 1.5 off to 2. That's going to be iron FeO2. That's my empirical formula. Problem is, that's not good enough. We clearly have a fraction here. And this would be the case if we had a fraction of a 1/3 or a 1/4. If we had something that was recognizable as a fraction, 0.333, 0.250, 0.5, 0.75, 0.666, something along those lines where we go, okay, there's clearly a fraction there. That's something that we have to go, we can't round this. If I have 1.1 or 1.9 or 1.87 or something along those lines, I can round that up. I can round that down. I'm probably close enough. But when I'm in that fractional zone where it's very, very clearly a fraction, I can't just simply round it off. I have to recognize that there's something else going on here. And so I've got a half. So I need to multiply both of these by 2 to get rid of the half. That leaves me with 2 iron and 3 oxygen. My empirical formula, Fe2O3. So when we're caught in that position, and this is common, halves and thirds in particular are quite common. If you see that, don't immediately assume that you have to round it. Take it to its natural conclusion, multiply by the number in the denominator of that fraction. So multiply a half by 2, a third by 3, and carry it the rest of the way. This Fe2O3, this is the correct ratio. All right, questions on this example?
No.
No.
Okay, let's take a look at this next one. We'll call it a day after this example. Structures containing the mineral magnetite are found in avian beaks, and they may help birds actually navigate. Magnetite is an oxide of an iron that is 72.36% iron by mass. What is its empirical formula? So the process here we're going to do is exactly the same that we did in the previous problem. We're going to start by converting our percentages into masses. And we're not told what the mass of oxygen is, but since it is an oxide and the other component is only oxygen, we can just take what is left. And so starting with these values, we're going to, again, convert them into moles, 55.85 grams in 1 mole of iron. And so 72.36 divided by 55.85 is 1.296. For oxygen, again, 1 mole of oxygen is 16.00 grams. And so 27.64 divided by 16 to 4 significant figures is 1.728 moles of oxygen. So again, we have a ratio here that is not apparent, but we're going to follow the same protocol, the same practice. We need to divide each one of these by the smaller of the two numbers to guarantee that we get the smallest one in the lowest ratio, which is 1. So we're going to guarantee that the iron is 1, 1.296 for the oxygen gives us 1.333 moles of oxygen. And so again, here, this is an example of where we have a third. And so since we have a third, we're going to need to apply a multiplier here. We're going to multiply both of these by 3 to get rid of that third, which means that we're going to have 3 irons and 1 1/3 times 3 is 4 oxygens. And so our empirical formula is Fe3O4. Now, the second question here is about its molecular formula. We're told that the molar mass is 231.5 grams per mole. So what is the molecular formula? Well, to find that, again, we need to be in search of N. N is calculated by taking the molar mass and dividing it by the empirical mass. So we had the molar mass, 231.5 grams per mole, and we're going to divide that by the empirical mass. Now the empirical mass, Fe3O4, 55.85 times 3 for iron, plus 16 times 4 for oxygen, gives us 231.55 grams per mole. And so in this case, we can see that these two numbers are pretty much the same. Our multiplier here is going to be 1. And so the molecular formula is the same as the empirical formula. Times 1. So Fe3O4 is also the molecular formula in this case. And that's possible. That is entirely within the realm of possibility, that you can have an empirical formula and a molecular formula be identical to each other. That happens all the time. But the way that we're sure is we have to compare the two to each other. We have to compare the mass of this to the mass that we know is the molar mass. And that's going to determine whether our empirical formula is our molecular formula, or if it's just a representation of the lowest terms of that molecular formula. And so that's really all that's going on there. Any questions?
No.
Okay, so what we'll be doing tomorrow we're actually going to be starting into chapter 3, and if you look at your post-lecture for overnight, you're going to see that there's going to be some empirical and molecular formula problems in there. This is on smart work. There will also be a little bit in there about light. If you've taken a physics class in recent memory, what you're going to find is that tomorrow and the next couple of days, we're going to be talking about electrons, and there's going to be a lot of interfacing between physics and chemistry that lead us to a lot of our understanding about light, matter, and electrons. And so a lot of that stuff's going to be coming together over the next couple of days. And part of that chapter 3 intro assignment that is piggybacked on that empirical formulas post-lecture is kind of getting you ready for that. So that's some of the stuff that you'll see tonight in the post-lecture materials. Don't forget also, the chapter 1 quiz is available today. You have to complete it by the end of tonight. So that's up there in Blackboard as well. And I will also be posting to Blackboard the other other lab activities for this week. I got a little bit behind in posting the empirical formulas one that you're doing today, but that will be up sometime this afternoon. That one is a formal lab report. So you'll actually have to, it won't be the Carolina report where you just kind of fill in the blanks in a couple of places. You'll actually have to do some writing for that. But I will be publishing a kind of a guide for what I'm looking for as far as that formal lab is concerned, in terms of, you know, what sections do you need, what do you need to be writing in each section, how many points are they worth, and how you'll be graded. So I will let you know when that comes available. I'll send you a message through Remind to let you know that that's there. And then if you have any questions about that, you can go ahead and just bring those up tomorrow or later on this week. Any final thoughts from anybody?